Hey there, it's Shannon Metchick-Myers, and today we are going over differential equations, or actually application problems that can be modeled using linear models. So this one is about interest, so let's check it out. When interest is compounded continuously, the amount of money increases as a rate proportional to the amount as present at time t, that is, ds dt equals to r times s, where r is the annual rate of interest. For this problem, r will be 5.75% interest. If you're in my class, you may want to have your 1.3 guided notes handy as to where these came from. We had kind of an intro as far as setting up models for DEs in that section. So for this one, we want to find the amount of money accrued at the end of 5 years when $5,000 is deposited in a savings account drawing 5.75% annual interest compounded continuously. So first, let's take a look at this differential equation. The instantaneous rate of change of the amount present in the account is, with respect to time, is r times s. Getting this into linear form, we have the variables s and t. So this would be plus negative r times s is equal to 0. And so over here, if you look at your integrating factor, because we have a linear differential equation, it's going to be e to the integral negative r dt, which is equal to e to the negative rt. So now, coming back and multiplying both sides by our integrating factor, we will have, remember, we write this as the derivative with respect to t of a product, both of them functions of t, so I'll have e to the negative rt times s. And that's going to still equal to 0. And then rewriting so that we can integrate, we will have e to the negative rt, it being integrated with respect to s is equal to the integral of 0 dt. And so we'll have e to the negative rt times s is equal to our constant of integration. Good so far? Okay, so now s will end up being, if we multiply both sides by e to the positive rt, and if we rename c to be S0, right, the initial amount, will have S0 e to the rt. And if you want, you could write this one as s at time t, the amount at time t. So continuing to get our general model, we will have s at t equals, so let's plug in what we know. We know that $5,000 is our initial amount from here, right? So we can plug that in for S0. And then we also know our rate, which was 0.0575 times t. So that is the model that we'll use. All right, so we also wanted to find out what s at 5 is. So I'll just plug in 5 wherever there's a t. All right, so looking at this on the calculator, we would need to have 5,000 times e. E is being raised to the 0.0575 times 5. And so after 5 years, we'll get approximately $6,665.45. So that finishes up part A. Now we want to find out, given these same conditions, in how many years will the initial sum deposited have doubled, right? So basically, in general, you can set it up as 2 times the initial amount is equal to the initial amount times e to the r, which was 0.0575 times t. And you see that the as zeros divide out, and we end up with 2 is equal to e to the 0.0575t. Applying the natural log to each side, we end up with natural log 2 equals 0.0575t, because when you apply the natural log to the natural exponential, you get what's inside the power because they're inverses of each other. And then bringing it back over here, we have that t is equal to natural log at 2 over 0.0575, and then grabbing our calculator again, we would have natural log 2, don't forget to close your parentheses on that, divided by 0.0575, enter. So that's going to happen in about 12 years, approximately 12 years. Okay. So that's how long at that interest rate it would take to double. So the initial amount honestly doesn't even matter. It's the rate. Okay, so now this one is if you were only compounding quarterly. So, you know, it's not as realistic, but it's interesting to see. So I set up the, you know, compounding quarterly situation for you. So we would have 5,000 times parentheses 1 plus 0.0575 divided by 4 raised to the 5 times 4 is 20, so I'll just evaluate that, and it's just a little bit less, right? So we would get compounded quarterly, this would end up being $6,651.82, and we're good to go. All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please hit that like button and subscribe. Bye.